hydrogen balloon, and in subsequent years we taught more teachers how to do that. We now have our own helium balloon program. Sometimes we use hydrogen. Hydrogen goes higher, but it's more volatile. We fly 3 missions a year, and we also 2 years ago first started putting teachers into flight, helping to test the Final Frontier Design spacesuit, which you see in this picture, designed and built in the Brooklyn Navy Yards, and we've been flying it on 20 parabola flights in Canada every November. So what we're doing is we're bringing real space activities, space science, space experiences into the classroom, giving it to teachers and enabling those teachers to share that with their students. We've been doing things with Skype. We've been flying experiments on the world's first stratospheric glider. We were doing that in Argentina last summer. We had a local technical school come visit, and we had Skype sessions going between those Argentine students and the New York students who built the experiment. And they talked to each other across that distance and across that language barrier, and it was really exciting. We do competitions, and as more and more flights become available to us, we don't have to do so much competition. It's not so much 100 people enter and 1 get to fly. Now it's 40 people enter and 10 get to fly, and that's pretty exciting. We're looking to the day when you want to build it, we can fly it for you. So where do we fly? When we first started to plan what we would fly and where we would fly it, we thought, well, you know, it's kind of a stair step. You can get on an airplane, you can climb a mountain. Perlin 1, this is a glider that set the world's record, and that record stands today. It was set in 2006 at about 51,000 feet. The new Perlin 2 glider is the world's first stratospheric glider. Just this year, last month, in Minden, Nevada, I think it reached 33,000 feet, and now it's en route to Argentina with our experiments aiming to beat this record. But, you know, we've leapt ahead. It turns out that we've already flown 2 experiments built by students to the International Space Station, and we get up to 20 miles, yeah, 20 miles on our high-altitude balloons. And tomorrow, if you don't already know, you're going to hear about Blue Origin flights. We're looking to start getting our experiments onto those next year. Okay, so right now, today, stratosphere is where we are. That's where our balloons go. That's where Perlin is headed. So that's the second layer of Earth's atmosphere, and not much goes there. So it's very exciting that students can put not just a camera, which you probably see on the internet all the time, but we're teaching them to work with Arduinos, and we're using 3D printers to make form factors of CubeSats. So if a normal CubeSat might be 10 centimeters, ours is 4, it's very lightweight, and we can fly it on a balloon. We can fly it in the glider. What I learned when I went to Argentina last year is that a tequila box is very useful. After you drink the tequila, you can put your CubeSat inside it. So yeah, like this is an example of a classroom-built CubeSat form factor. And this one, we have 10 of these, and sometimes something gets damaged, and I'll say, oh, here, take this piece. So this one's been taken apart a little bit. There used to be another platform up in here. They're devised so that if you want, like when it's flying on a balloon, you can put your little lithium-ion battery. These are last year's model. They're soft-shelled. There's a new model this year which is hard-shelled, so that's better for high altitude. Slips under here. This is an Arduino Uno processor board with data store, and it's standard. You can pull the data chip and put it right into the chip reader on your laptop. So you get your data. If it's a balloon, if it's a glider, it lands. You take your experiment out, you pull your data, and you email it or you upload it to the web. It's instant, right to the classroom. This one has a pressure sensor built into it, which is useful for determining altitude, right? You can just look at a chart and see, well, if the pressure is this, I must be at that altitude. You can check for things like carbon dioxide. You can check temperature. You can check radiation. We've got a couple of these we put Geiger counters in. So more about that. Let's see. Okay. Yeah, high altitude balloons. This is what a high altitude balloon looks like when it reaches the top of its flight, because what happens, it expands as it gets into lower pressure until eventually it bursts. And this image is the moment of burst where the balloon just comes apart like ribbons, and then it comes crashing down to Earth. And if you have packed your payload carefully, you'll be able to retrieve it, everything will be fine, and you'll get your video and lots of very interesting data. And the last line up there is the URL for our High Altitude Achievement Club, which is at Gloversville High School, upstate, not far from Syracuse. And if you're interested in flying stuff, they are available. They will teach you how, or they will do it for you. Okay, so this is the glider. The glider is backed by Dennis Tito and by Airbus. And it is built specifically to go to 90,000 feet. It has a 90-foot wingspan. And what you see in this picture is the tow plane. That's the one that has the bigger wheels and the thicker wings, slightly to the left. And then this gorgeous thing that's all wing is the glider. And we got to see it fly. We got 5 good test flights in Argentina last year, flying our experiments. And it's heading back there now. It takes a long time. It goes by boat and then by truck until eventually it gets to El Calafate, and the wings get put on and they'll start flying again in September. This is the one we're really excited about. So what have I been doing for the past month? Writing our flight opportunities proposal to see if NASA will give us some money to put some of these experiments onto Blue Origin's New Shepard and actually get our suborbital flights for our experiments. So exciting. They've already done 5 successful test flights, and if all goes well, we will be able to contract for our flights, maybe sign a contract in March for September flights. And they're going to go 3 times as high as we go today. They're going to go not 20, but 60 miles. Okay, so I just showed you what this thing looks like, and this photograph of our form factors. The first line is wrong. The form factor, obviously, is 4 centimeters on a side, 3D printed. And yes, it does weigh less than 2 ounces. With the Arduinos in it, it's 4 ounces. And it models the 10 centimeter per side CubeSat that's more common in space applications. So we do often partition these. When the second partition is up here, you can add another experiment. So we've had schools do Geiger counters in one section and Wisconsin fast plant seeds in another. Fast plant seeds, you can buy them from Amazon. They have a 29-day life cycle. So they come with instructions on how to build the proper lights so that you can grow them 24 hours. And they will go from seeds to plants to your next generation of seeds in 29 days. So you can quickly see whether, or try to see whether there's any impact to things that you do to them, like flying them for long times on Stratosphere gliders. And so we have built a cabinet that we put our CubeSats into to protect them and to fly them on the Perlin glider, and we're looking at the Blue Origin and NanoRacks payload guide to see what can we do with them, and that's very, very exciting. Okay, so typical flight experiment components. If you are a classroom, you can buy this stuff from SparkFun, from Adafruit, from Amazon. Sensors can be as cheap as $20. You can buy most of this stuff for about $500, so it's super affordable and the sort of thing that teachers can easily do a GoFundMe or a Donors Choose. If you're a public school teacher, Donors Choose is so that anybody can donate money to help you fund your project, and a lot of our teachers fund their projects that way. So you pick and choose the components you want, and you snap them onto your breadboard, and you download the software from the Arduino website, and you start making your program, and you're able to build an experiment. Okay, then what? Well, then you have to be very careful if you're flying it on a balloon, because a balloon takes about an hour and a half to wander upward to the top of its flight, and then it bursts and comes crashing down. It takes about 30 minutes to come back down again. We're almost entirely East Coast. I'm here in New York City. Our balloon program is upstate. Most of the core team of teachers are around the Connecticut and Virginia area. We have hills, we have trees, and we have water. And we also have airspace where you don't want to fly. So, you know, we're somewhat limited where we can fly these balloons, and you really want to be careful about the conditions you're going to be in when you're payload comes crashing down, we have a climber on our team now, because sometimes it takes 24 hours to get up in the tree in the national park where the payload landed. It's way more fun to fly in Mojave Desert or tobacco fields in Georgia. It's much more instant to get your payload there. Okay, this is payload integration for the Perlin, so a little more complicated. The Perlin glider has a payload bay cut into its tail, and that's where we can put our cabinet, which holds 4 of these. And one of the things that we did was to remove the batteries from the individual experiments and build a battery bay into the payload cabinet. And that's because when we built this thing for last year, these soft shell batteries really need pressure, especially as they get into the upper atmosphere, into the stratosphere. And so that battery bay holds them tight. That's not so important this year when they have hard shells. And we're looking to eliminate that when we switch to Blue Origin, because Nanorex has built a feather frame that has power and data connections to the vehicle, which is really exciting for us. One of the things we're working on is how do we work with that? Today, you want to put this on a balloon, you want to put it in Perlin, somebody has to be there to manually turn it on and load it in. And one of the reasons we chose these batteries is that they give us enough power for a 7-hour flight on Perlin if necessary. That's how long it could take once they start going to their full altitude. So it's a lot of learning opportunities for teachers and students about the difference in flight profile and in payload integration and in the technology available between a balloon, which has no systems of its own. Everything has to be built into the payload. Communication, tracking, data store, power, all have to be in your payload. Perlin, it's a plane, it's a glider, there's a pilot, there is a certain amount of data captured from the vehicle's own systems, and that's available to us, but we don't integrate with it. So you still have to build your own power supply and your own control for your experiment. And with Blue Origin, we may be able to integrate with their systems. And so that's a whole interesting new area of learning and work for us and for our teachers and students. Next. There we go. So this is an example of Perlin's own ground crew procedures, just to show that it gets more and more complicated, right? Going from all we're doing is packing our cubes safely into the locker and making sure that the power's on. They have to do things with their computer, with their GPS. You know, it's very critical that all their systems be working, and this is part of what we teach our teachers and students. And this I stole from Blue Origin as I was working on how it is that we're going to adapt our locker to fit into what Nanorex will provide on Blue Origin. You can find this on their website, and it's really exciting because it's real, and they're going to be flying next year with payloads. These are the teachers from last year. We opened up, this was a contest where we said you don't have to have attended one of our workshops. This contest, we said just send us a proposal. And we set up engineering gates. There were phases each month. We had a crew of 10 judges, some from NASA, some from universities, some from industry, who looked at the proposals and made sure that they were progressing properly. So we went from proposal to design and eventually selected 10 for build, and 9 were delivered. So, you know, it's an interesting lesson in how people progress, who drops out and why. But we got 9 good experiments last year, and we added 1 more this year, which is why you still see 10 on here. Over on the top right corner, Bismar Rossi is the professor at the Argentine Technical School. So we added him because one of the experiments that flew, the one that's with Jim Cool there in the Final Frontier Design spacesuit, Jim's in Syracuse, and his students, his 6th graders, wanted to fly extremophile moss, which they think would be good for terraforming Mars, and they worked with a SUNY moss professor to make sure this was good. But we didn't see how we were going to get our moss between New York and Argentina and back, and so we connected with Bismar, and his students chose Argentine moss, and we flew that. So there was a collaboration between those 2 schools, which was really cool for everybody. This is when Dennis Tito did the ribbon cutting for the hangar that he built in Minden, Nevada for the Perlin glider, and I'm there on the left, and then there's president of Airbus, who is a big sponsor, and Ed Warnock standing there with a microphone. He's the CEO of the Perlin project. And then you see Morgan Sandercock is one of the pilots and engineers, and then Dennis, and then more pilots and engineers. So it's really an exciting project because this is a brand new vehicle and they're still doing their test flight profiles. They're totally open to teachers and students coming to visit, and we just took a crew of 3 teachers there last month, and they blogged about it, and they did video interviews with people, and they went on a glider flight. And it's so exciting for them. Can't wait to do it with suborbital vehicles. So yeah, here we are Skyping in Argentina, showing off our CubeSat to the Argentine students who came to the hangar there, and on the laptop, talking with us are the students in New York. This is the electronic schematic for our dual Geiger counter experiment. We have 2 versions of this. This is the one that was built to fly on Perlin last year. This year we had a contract with the Ashford, Connecticut school. Normally we work with high school teachers. This school asked us to come and teach a 6-week course to a group of kindergarten through 8th graders and their teachers. And they said, don't try to teach us Arduino programming. Teach us about what you've already done. And then help us design a version of that you can fly for us. So they really liked this Geiger counter experiment, and we built a new one, and they got to practice with the 3D printing, and they got to practice putting the components together. And we did a lot of tests in the classroom with a big Geiger counter and some radioactive materials, and how well does it get protected if you drop it in water. Surprise, you know, put it in a bin of water, you get a much lower reading on the Geiger counter, so the kids could really see this stuff work. We flew their experiment already this year on the balloon, and now it's headed to Argentina, where it and last year's version will both fly on Perlin. The teachers get their data back right away in a format that they can drop into an Excel spreadsheet. So here's an example of how the data looks in table format coming back from a glider flight, and you can find this on our website. And here's how it looks when they make charts of it. So the one up on the upper left corner is from last year from the glider flight, and the one here is the balloon flight. Much shorter, up and down quickly, as opposed to the glider, which glides and stays at the same altitude for a much longer period of time. So it's really interesting. What they're doing here is protecting one Geiger counter with some type of protective material and leaving the other one unprotected, and it shows that in both cases, the protective material, which was a new one in the upper left corner from a fabric developer, and in the right corner on the balloon with the kids, tinfoil. It worked. And so what can you do? You can bring TIS to a school near you. Go to our website. It's teachers-in-space.com. You can find out how to get in touch with me, and you can help us get contracts at schools. You can help us figure out how to take advantage of Mark Jackson's fabulous crowdfunding opportunities that we never seem to have time to do, but we really want to. And if you want to help us fly stuff, we would love to talk to you.
Thank you very much. I was weak and I could not stop you. So
am I way over? I set my timer and I'm sorry.
It's okay. But we have time for one question. No question? Yeah, there is one. Yes.
Is there a set size on the CubeSat? Is that a standardized thing?
It is, yeah. We chose this standard because it's what the suborbital providers were looking at, and that way, no matter which one you fly with, it should fit. And we probably got this from Nanoracks. I'd have to ask my engineer for sure, but he was like, yeah, I knew this was the right size. And so that's the point, right? To be able to create standards so that one classroom can do what another classroom did. Teachers can go to conferences and work on this together. And all that you should have to care about is what's inside it. What do I want my experiment to do? And don't spend all the time we used to spend the first few years on what do I pack it in? How do I fly it? There's providers who can do that for you, and now you can just focus on the science. Thank you.
Okay, thank you very much.